Are we live?
Live, all right.
So this is for Quentin and Amy. All right, so welcome to quarter 4, electromagnetism. So electromagnetism has 3 units: current, circuits, and then magnetism. And at the end, we'll have a little solar project. It'll be great fun. So electric current, this is probably the one thing that you've been most exposed to in your life. It's electricity. It's the movement of charges. One thing that's really important is the idea of conventional current, and that is positive charges moving. And I don't know why everyone decided to make it this way, but in conventional current, positive charges move from the positive to the negative. They leave the positive pole, they go to the negative pole. It's really strange, but that's what they do. Realize that positive charges don't move, electrons move, and they create electric fields, but that's what they mean by conventional current. Now, when we are looking at circuits, there's 2 types of circuits. There's a series circuit where current moves in one path, and there's parallel circuits where current moves in multiple paths. So if you have a series circuit, there's one loop from the source of the potential to the wherever it's going, and then parallel, there's multiple paths. Additionally, we have 2 types of current. DC circuits are direct current, where all the charge goes from the positive to the negative. One loop. In alternating current, it goes from the positive to the negative, and then the positive-negative poles switch, and it goes from that pole again, positive-negative again, but the poles are constantly switching. So DC current's like we're moving one direction, AC current is moving in this way, then we're moving this way, then we're moving this way, then we're moving this way. The movement of charges is what's important. You have to have a movement of charge, but it doesn't all have to go in one direction. This is what Tesla figured out. He said, well, we could actually just like move it there, move it back, move it there, move it back, move it there, move it back. And that becomes very efficient when you're trying to use objects that like current to be changing, which are like motors, generators, which we're going to talk about later on. Okay, so most of what today we're going to talk about is capacitors. Capacitors are things that store charge. And they're the kind of bridge between electrostatics, which is what we learned when we did field forces. Positive charges getting stuck, negative charges getting stuck. Coulomb's law, Fe equals K Q1 Q2 over D squared. Okay, so it's a bridge between electrostatics and electric current. So any questions before we jump right in? Okay. 2 important formulas, V equals IR and P equals IB, which we're going to get to. All right, so let's talk about the capacitor. This is how a capacitor works. You have 2 pieces of metal, and you connect to them a voltage source, what we call potential. By the way, when we're talking about current, you have to have a voltage source or a potential source. That's like a pump that pumps the charge in one direction. With a battery, it's an electrochemical cell where there's a redox reaction. There's a redox reaction where the electrons want to move from one side to the other to make the products and consume the reactants. That's the potential. With a generator, you have an electric and a magnetic field that creates a potential. But either way, you attach a potential to 2 metal plates. And what that does is it causes the charges to separate, kind of like with the electroscopes, but really, really strong. Remember how we rubbed the fur on the PVC pipe and like the charges separated? Well, that's what a capacitor does. You attach it to a voltage source, and it pulls the charges away. In this case, the positives are being pulled away this direction. In this case, the negatives are being pulled away this direction. And that causes a huge charge separation. Now, when you short that connection and give it somewhere to go, those charges are going to equalize. The plate that has way too many positives are going to go through and neutralize some of the negatives. And the plate that has way too many negatives are going to go through and they're going to neutralize some of the positives. Charge flow. The flow of charge allows us to do things. Like put a battery in there. The one place where you've probably seen a capacitor, I think this one works. was trying to play with a bunch of these and try to get it to work, and some of them were working, and some of them were very much not. You hear that? Okay, so these are disposable cameras. They were a big deal about 30 years ago. And what they do is they have a little circuit board and then this single AA battery. And that single AA battery charges a capacitor. And that capacitor gets charged up and then dumps all of its power all at once. Because when you short a capacitor, those charges move real fast. And this single AA battery would never make enough power to cause that flash. But you let it build and build and build and build and use the AA battery to pull the charges and pull the charges and pull the charges, and then they dump. Here we go. Separate, 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 separate. And then dump.
I looked away that time.
So bright.
Yes, it is. What's another place we might use a capacitor? Where you want to build up charge, build up charge, build charge, and just dump it. Last November, they tore up the strip and they laid down new concrete and asphalt
Explosions.
for F1, because F1, the race cars, they have a little capacitor. It's a big capacitor, and what they do is when you press on your brakes, just like our Teslas, it brings back charge, but they don't dump it into a battery, they dump it into a capacitor. And then when they're driving along and they hit the button, the capacitor dumps the battery, the energy back into the generator, and it gets a boost. And bananas. But yeah, capacitor's kind of like if you had a bucket and this was the only source of water you had, but you really wanted to like douse somebody. You're like, hey, come here, I'm gonna get you a little wet. Well, it would be more effective to just fill up a bucket and then dump it on somebody. That's what a capacitor does. It builds and builds and builds and dumps. It also makes sparks. Unfortunately, the one that I have, the ones that make sparks, I don't know why they're not working, but yeah, I have a bunch that make sparks, but they're just not, they're not cooperating with me. So I'm going to give it one more try. This is a capacitor bank. This capacitor bank will hurt you bad because that's a lot. These capacitors are all linked together, and I made it for an electric bike, an e-bike, not a bike that uses electricity, a bike that creates electricity. And I'm going to connect these batteries together. By the way, these are 9-volt batteries. They're called batteries because they are 6 1.5-volt cells.
Why are AA batteries and AAA batteries round? Those are square.
Round have the most volume per unit surface area. So round is good. And these are square because there's 1, 2, 3, 4, 5, 6 tiny cells in them, which allows them to produce 9. So the typical alkaline electrochemical cell is 1.5 volts. A AA battery has 1 of them. A 9-volt battery has 6 of them. 6 little ones all wired together. Yeah, we're going to play a lot. So, and then if you connect batteries in series, one of the things we're going to find out is we can add their voltage. So this is a 9-volt, exactly, this is a 9-volt battery. This is an 18-volt battery. This is a 27-volt battery. And I'm going to connect that 27-volt battery to my capacitor, my bank of capacitors. So I'm just going to touch it. And what's going to happen is you don't see it, but the capacitors are charging up. They're causing charge separation to happen as the positives pull the negatives away and the negatives pull the positive away. And then after some time, this is a fully charged capacitor.
Smart.
Yeah, these things are just toast. If I give it enough, if I give it a reason to travel through, they're like, we want to go, we're too built up. And they go. One of my favorite places where you're going to see a capacitor is in the sky. Because the clouds get a charge separation. And if the charge separation gets large enough, the spark will jump, just like this. This is not very much energy, but if I was to touch between those and give the electricity somewhere to go, it would kindly travel. But if I get it close enough together, it'll make the spark. Yeah. Could you see what color it was?
Green.
Yeah, it's green. Why is it green?
I'm sure there's a reason.
It's because these are tin-coated copper. These connectors are tin-coated copper, so we're basically seriously cooking off the copper. And when copper ions get energy, they turn green. So that's what a capacitor is. Pretty cool. Now, this is everybody's favorite part of the investigation. You've probably seen these tiny capacitors before. In old electronics, this is what they look like. This is literally two pieces of metal with what's called a dielectric in between. So you have two metals separated by a dielectric, which is an insulator. Because if you create charge, those charges want to travel back to each other. You need to put a good insulator in between. And how strong your capacitor is going to be is based on how good your dielectric is. So these are the old style capacitors. These are literally a strip of metal about that long and about a centimeter, roll one metal and then a piece of paper, another piece of metal, rolled up together. What I'm going to do is I'm going to give it way too much, so the dielectric fails. I'm going to make it fail over here. I'm going to make the dielectric fail on purpose.
I don't know what this does.
So right now, this is how many volts?
27.
27. And now how much?
36.
36. I think I have one more the other day. We'll just go with 36. We'll see what happens. So, oh, by the way, on 9-volt battery, the narrow one is the positive. Sometimes they even, yeah, the fat one's the negative. So I'm going to connect. I might get another one just in case. We'll see. Okay, so there's my positive. Here's my negative. Okay. Now, if I connect these two together, charge will flow, but not very fast. It'll go real slow. Yeah, so I got a 36-volt battery here, and I'm going to connect this to a capacitor, which is rated at 10 volts. So that capacitor rated at 10 volts, meaning the dielectric is only good enough to hold 10 volts beyond it. And if I give it 45 volts, the dielectric just fails and it explodes. What the explosion was is just burning paper, because the dielectric is paper, and you just burn it, and then the smoke has to go somewhere. Out it goes. Yeah, pretty fun. So yeah, want to do it again?
Yeah, sure.
Now this is, we found out last period, this is interesting. I can use that was a 220 microfarad capacitor. We'll explain what that means again. So that small one was a 220 microfarad capacitor. This next one is a 470 microfarad capacitor. And no big surprise, the 470 is bigger by just a little bit.
Is that just like another unit of?
Yeah, we're going to talk about that. The farad is named after this guy named Michael Faraday. So it's still a 10-volt capacitor, meaning that the dielectric is only good for 10 volts, but it's a little bit bigger. It's got more stuff wrapped up in the thing, but a wee bit bigger.
Oh my god. It's like a confetti gun.
Yeah, exactly. Oh, yeah. Zip, zap, zap. This actually, it's like zap, zap, zap. But yeah, so, okay. So that's how a capacitor works. It stores charge in an electric field because anytime you have a positive and a negative, an electric field is created. In other words, there's an electric field pushing from the positive to the negative. And the only thing that's keeping that electric field stationary is that dielectric. And there is some math, because of course there is. Ooh, all at once, okay, yeah. So capacitance is given the unit of farad, and the farad is equal to 1 coulomb of charge stored by 1 volt. So remember, a packet of charge is a coulomb. Like the electron has the fundamental charge, so 1 electron is 1.90 times 10 to the negative 19 coulombs. So the coulomb is charge. A single farad is what you would get if you were able to start charge or able to store a coulomb of charge in 1 volt. A farad is a massive amount of capacitance. Like 1 farad capacitors are about this big. Yeah, those go, they'll take your house down. So usually we use microfarads because a single coulomb is a ton of charge. So being able to store a ton, like 1 coulomb in 1 volt, is a massive amount of charge. So usually what we use is the microfarad and sometimes the nanofarad. So they'll charge maybe 10 to the negative 6, 10 to the negative 7 coulombs. That's the amount of charge we can handle. You're talking about a full coulomb, you're talking about like lightning bolts. Okay, so here's the formula. Charge, the amount of charge you can store, is equal to the capacitance times the potential, the voltage. By the way, potential and voltage, they're the same thing. Voltage is like a slang term for potential. The potential to move charges is voltage. We'll talk more about that later, but this is kind of weird and out of order. We had to start somewhere. So the amount of charge you can store is equal to the capacitance, the storage, and how much you're pushing into the storage. And then the capacitance itself is based upon K epsilon naught. K epsilon naught is the dielectric constant. So K is the dielectric constant, how good the capacitance is, or how good the dielectric is. And epsilon naught is how strongly an electron can push through it. So epsilon naught is a constant because it's only electrons that are pushing through. If we use some other particle, it would have a different epsilon naught. But we're using electrons, so epsilon naught is how strong the electron can push through, and then K is how well the dielectric can hold those charges out, pull the charges back. A is the area. D is the distance between them. We have a simulation we're going to do tomorrow that's really great. Let's simulate this. Okay. There's a formula for energy, U, that we're going to use a little bit. Not right now. We're going to learn a little bit. But when you use that formula, we're going to learn later, and you plug it into this formula, what you get is the energy stored in the capacitor is 1/2 CV squared. The energy stored in a capacitor is 1/2 CV squared. Because the energy in an electric field is equal to the volts and the charge. So when you substitute the volts and the charge in for the charge, you get energy is 1/2 CV squared. You know what else is 1/2 something squared?
A lot of things in this class.
Yes, a lot of things. So the energy in a capacitor is 1/2 CV squared. C is storage. V is how strong you're pushing in that storage. Remember this? Exactly. Just pretend I'm writing the word spring. Spring is 1/2. You want to remember?
Kx squared.
Kx squared. K is the stiffness of the spring, and X is how far you pull it. They're analogous. The amount of energy you can store in a capacitor is equal to how well that capacitor holds charge and how strongly you push the charge into the capacitor. Potential energy of spring is equal to 1/2 the stiffness of the spring by how much you pull on it or push on it. So capacitance is basically potential energy. Fun part about capacitance, though, is you can dump it really fast. Okay. Questions? I think that's everything for capacitance, just formula, or just practice now. Oh, yeah, this is also important. Okay, so these are all capacitors. This is a variable capacitor, which is bananas. It allows you to twist it and change how many plates are in the capacitance. So here's how this works. If you have two things lined up with each other, that's a series, one after another. Kind of like the serial, like a TV show is a series, one builds on the next one, builds on the next one. So if you have two things together, they are in series. If you have multiple paths, they are in parallel. So imagine you had a bucket. So imagine Sam has a bucket and Hannah has a bucket. And you both fill the buckets up. And then you go find TJ and you both dump your buckets on TJ. You get them with a lot of water, right? That would be like parallel. You have two buckets that are independent of each other. In series, however, Sam would have an empty bucket and Hannah would have a full bucket, and Hannah would dump her water into Sam's bucket, and then Sam would dump it on TJ. So the overall capacitance, how much you can dump, is actually smaller when you put capacitors in series. The formula is 1/C equals 1 over plus 1, and so on. So if you had two 2 farad capacitors in series, you would have 1/C series is 1/2 plus 1/2. So how much capacitance would you have if you had two 1 farad if you had two 2 farad capacitors in series? You got a 2 farad capacitor. So this 2 farad capacitor is connected to this 2 farad capacitor. What's the actual capacitance value? 1. Yeah. So if you have capacitors in series, the overall equivalent capacitance is 1 farad. However, if you put them in parallel, 1/C parallel, oops, not C, it's just C parallel. If they're in parallel, it's C parallel equals C1 plus C2. So if both of the capacitors were loaded up and they were both 2 ohm or 2 farads, they would have an equivalent capacitance of how much? 4. Get the idea? Yeah, it's like, I find the water analogy doesn't come up a lot. It's like you're filling one bucket to the next bucket. It's not very efficient. If you both have 2 full buckets, then bam. So if they're in parallel, then you get the sum. If they're in series, you get the sum of the reciprocals. And now let's do some exercises. Then we'll be done for today. Disconnect you guys. By the way, this drains them really fast. If you just go stick them and get warmed up and they melt. Anyway, how much charge in coulombs can be stored in a 10 microfarad capacitor? Microfarad, when connected to a 25 volt source. So go ahead and bang that out. Or do it in your head, it's up to you.
Of course.
Sam, do you want one?
Sure. Thanks, Kim.
By the way, if you get some old disposable cameras, don't throw them away. Because this capacitor is no joke. I went to charge the capacitor, and I gave it to another physics teacher, and he didn't realize it was charged, and it shocked him. Whoops. Should have told her it was charged.
Whoopsies.
Yep.
So what's the farad mean again?
It is the quality of the capacitor. It's the size of the bucket.
Okay.
Now, again, those like round capacitors are called electrolytic capacitors. Their quality, their dielectric is crappy, but they're cheap. The capacitors that have a metallic tip, like these guys are just, ugh. That's what I fried. A 10 microfarad 25 volt capacitor. The ones that have like a metal cap, look like a metal cylinder, those have a much better dielectric, so you get a much higher capacitance for a smaller area. They have a much higher K. The good capacitors have a very high K. In fact, when you buy things, like you go buy a motherboard or a CPU, they're like, we're using high K capacitors. That's what they mean. I mean a very good dielectric, so it's very it's efficient. All right, so it's pretty simple. Our formula is the capacitance equals, charge. I got that. Well, that's another thing. In current and circuits, the variable and the units are really tricky. Capacitance has the variable F, the variable C, the unit F for farad. Charge has the variable Q and the unit C for Coulomb. I wasn't there when they made the rules. Just be really careful. There is one good news. Potential has the variable V and the unit volts. So that's why it's called voltage. Anyway, so your formula is just the amount of charge you can store is equal to the capacitance times the potential. And the capacitance is 10 times 10 to the negative 6 farads times 25 volts. So 250 times 10 to the negative 6, or 2.5 times 10 to the negative 4 coulombs. Is that what you got? Yep. And then you can look at area. It's like, hey, how much capacitance exists in a capacitor of a rolled up foil surface, which is what they are. In fact, I actually have one. While you're doing this calculation, I will show you. Oh, there it is. There it is. I can actually take these electrolytic capacitors apart by just cutting them. So they have a thickness separation of 0.133 millimeters. Remember, that's millimeters. Everything in physics is standard units. So how do you go from a millimeter to a meter?
Times 100, or the other way around.
Divide by milli is not 100, centi is 100. Divide by 1,000. Divide by 1,000, because a milli is 1,000. There we go. That. Now we have to remove that little aluminum jacket. Not super easy to do.
What's the second one?
Yeah, that's what I'm thinking. Well, where's the 3.61? Is that the K?
Mm-hmm. Dielectric. I spared you the units of the dielectric, but basically the units of the dielectric just make the formula work. They are farad per meter. So to make all the units work, formula is C equals A epsilon A over D. So this unit right here needs to be farad, and then meter comes over, and meter squared is there, so it's farad per meter. Oh, it has one nasty pattern. Phew. What did you get?
5.28 times 10 to the negative 8.
5.28 times 10 to the negative 8. So 528 microfarads. Is that what else got?
Yep.
Okay. That's how it works. Oh, we don't have to do this one. But if 3 of the above capacitors were connected in parallel, how would you find the equivalent resistance? If they were in parallel.
Times 3.
times 3. Add them 3 by 3. Well, capacitor, capacitor. And if they were in series, then you would add their
One
watts.
over
Three
them.
times that.
Yeah, add their reciprocals. And I think, okay, last thing, how much energy? I didn't hit it, did I hit it with a 36? I did. So when I hit this thing with a 36 volts, the 10 microfarad capacitor, how much energy did I store in the thing before it popped? Just having the dickens of a time getting this aluminum shell off. Maybe if I connected it to a high voltage source, that would definitely do it.
So you get 3.6 times.
Definitely did not get that.
The first one.
It's charged. I think it's the bottom one.
That's the bottom one. It's like I'm peeling like a can of sardines. Go. Ha!
You get that number?
So
Yeah.
this is what the capacitor looks like inside. It's metal, paper, metal, all rolled up real tight.
So what you get?
0.006, right?
I mean, I did the 10 times, because like the micro microfarad.
It's times 10 to the negative 6.
Yeah.
So yeah, exactly 10 times 10 to the negative 6 farads times 36 squared,
0.00648.
0.00648
648.
joules. We're back to our standard unit of energy, the joule. A joule. All right, and that is. Oh, here's my capacitor slowed down to 80 frames per second. I didn't do this, but I found it online.
It's like a rocket ship.
Because all this is seriously, it's just smoke. We're burning off the paper dielectric. You see the paper dielectric, and the smoke has to go somewhere, so it does that. The second one we did actually did this. It blew off. We did this during. Here we go. We did this during chemistry AP because we were bored, and this is actually what we found. It actually did that.
Oh.
It didn't actually blow this apart. It just kind of launched. That's a bit of rocket. If you can do a rocket. All right. Questions? All right, we're done. Hopefully, Quentin and Amy actually watched the live stream.
Are there assignments today?
I'm sorry?
Are there